Okay, so I'm going to be talking about my probably favourite problem at the moment, which is the distributed Lovász Local Lemma. So I'll start on the Lovász Local Lemma part and then get the distributed part later. Lovász Local Lemma, it's originally and primarily a probability inequality. So it's the setup is you have some random variables, so for example these dice here, and you've got some events that can occur based on these random variables. And we'll say there are n of them, and these are bad things. So the point of the local lemma is to avoid stuff like these three dice having an even sum. That's bad for some reason. We don't want that to happen. We want to try and avoid this. And you can have a bunch of these events all based on some of your underlying random variables. And we ideally want to avoid all of these things from happening. These are bad. At the moment, that's not the case. We have some of these events that do happen. So for example, like on the left there, those three dice add up to 6, which is even. That's something bad. That's something we want to try and avoid. So what could we do? Well, if we can roll the dice, we'll just throw some dice again, hope that the situation has changed, and maybe some of these events are now no longer satisfied again meaning bad. And we can keep doing that until all of the events are no longer satisfied. And then we're happy. But when is this actually possible? It's not clear that you can necessarily get to the situation where all of these events is avoided. And that's where we have to actually have some probability and some parameters. So assume that there are n bad events, and we have this situation where the bad events are not all like totally dependent on the same stuff. You've got a wide array of underlying random variables. The events depend on some of the random variables. So only some pairs of the events depend on each other. Some of the events are independent from each other. So like on here, the one on the far left was independent from the one on the far right, because they didn't depend on any of the same dice rolls. And we'll say that each event is dependent on at most d of the other events. And also we need some bound on the maximum probability that any particular event occurs. And obviously this p is going to have to be less than 1 if we want to get anything reasonable, because if an event occurs with probability 1, then we can't check to avoid it. So assume that there's some bound p, which is strictly less than 1 on the probability that any of these bad things happens individually. Okay, then we want to ask, when can we avoid all these bad things happening? When is there a non-zero probability, if we sample our random variables, that we will avoid all this stuff, or equivalently just an existential statement? When does there exist a way of setting all these dice, not rolling them, just cheating and turning them to the number we wanted? When is it even possible to do that? So does anyone know any situations based on n, d, and p where we can be sure that it's possible to avoid all bad events?
No one knows.
No one knows? Yeah, so there's a couple of simple things that that we should know. Union bound, if we use a union bound, for example, we can just sum up the probabilities that each of the events happens. And if NP is less than 1, then we'll get the total probability that any of these happens is at most NP. If that's less than 1, there is some non-zero probability that none of them happen, and then we're happy. So that's one situation where it is possible to avoid all the bad events, and if we sample all the variables, roll all the dice, with some non-zero probability, we will avoid all the bad events. Second thing we know is if we have independence between all the events, so if d equals 0, and each event is dependent on 0 other events, then we can bound the probability that any of them happen. It's like 1 minus p to the power n. We don't need to do that calculation. We just know that it's not 1. There will be some non-zero probability that none of the events happen if they're independent, because the probabilities just multiply together. So in both of those cases, we know that it's possible to avoid all the bad events. The Lovász Local Lemma gives us a third way that we can know when this is possible to avoid all the bad events, which is kind of a trade-off between the two. So this is the original statement by Lovász and Erdős. And it basically says that when, I don't care about the constants here because I'm a computer scientist, not a mathematician. So when p is like inversely proportional to d, then we can also avoid all the bad events. So it's better than a union bound, which had like Pn had to be less than 1. Now we just need that Pd had to be less than 1/4 in this case, where d is the dependence degree, which is at most n, but it could be a lot less than n. So if your events are mostly independent, but a few of them are dependent, then this bound gives you something that's better than a union bound. And this bound was slightly improved in terms of constants over some subsequent results. This is kind of, in some sense, the optimal criterion here due to Shearer. But as I said, this is just a constant improvement. For the rest of the talk, I don't really care what that constant is. Okay, so that's the statement of the Lovász Local Lemma. I'll give you an example of when it's what it's useful for. It's useful actually, though it's a probabilistic statement. It's often used not for things that end up being probability. It's used to show the existence of things, just as an existential statement, using the probabilistic method. So one example is if we have a K-SAT formula, so some big formula in CNF, where each clause has K literals, and we also impose this condition that each literal only appears in at most just under 2 to the K clauses. So you can't have any literal in too many clauses. That's an extra condition we're imposing. In this case, we can show that this formula must be satisfiable. And the way we do that is that we can assume that we'll just randomly pick the values of each literal, true or false, uniformly random, and then use the Lovász Local Lemma. So our bad events now in this case are, there's a bad event for each clause. That is, if that clause is false, that's bad. That's what we're trying to avoid. And if we manage to avoid making each clause false, then all the clauses must be true, and then we satisfy the formula. Okay, so those are our bad events. If we avoid them all, we're happy. And we have this bound on the dependency degree. So because we know that each variable is in at most 2 to the K over EK clauses, and each clause contains at most K variables, if we multiply those two together, we get that each clause shares variables with at most 2 to the K over E other clauses. Okay, and that's our dependency degree D there. And we also have a simple bound on the probability that any bad event happens, the probability that a clause is false, which is precisely 2 to the minus K, because you need one of your literals to be true. Each of them is true with probability 1/2. So the probability that a clause is bad is 2 to the power minus K, because K is the number of literals in the clause. So we have a bound on D and we have a bound on P. And then we just plug that into the Lovász Local Lemma. We can see here that because we deliberately chose this value at the top here, 2 to the K over EK, so that these things multiply together to get E, that we have the condition. Sorry, 1 over E, that we have this condition. And then the Lovász Local Lemma just tells us this formula must be satisfiable. Okay, that's great to know. It doesn't necessarily really help us because maybe what we want is actually to find a satisfying assignment. The original proof of the Lovász Local Lemma didn't really help you there. It's a non-constructive proof. But since work on the Lovász Local Lemma has given algorithms for actually finding an assignment under the conditions where the Lovász Local Lemma tells you there must be one. And that's usually called the constructive or the algorithmic Lovász Local Lemma. And in particular, one of the most famous algorithm for this is Moser and Tardish's algorithm, which won the Gödel Prize in 2020. And it's very simple. It's basically just what I did in this example with the dice before. And that's that you sample all your variables, you roll all your dice. If any bad event happens, you just look at the variables that bad event depends on, and you sample them again. You just re-roll them. And you keep doing that. And you stop when all the bad events are not satisfied. Now, that's a very simple algorithm. We know that there must be a situation in which all the bad events are avoided because the Lovász Local Lemma tells us so. What's much less clear is that this algorithm actually terminates in any reasonable amount of time. It could be that you're rolling forever, or at least for an extremely long time. And that's the difficult proof that Moser and Tardish got this Gödel Prize for. But it turns out after not that many re-rolls of your dice, resampling step only NP, you will find in expectation, you can get a bound with high probability with a few more resampling steps. You will find a setting of your variables that avoids all the bad events. Okay, so there is a simple algorithm, at least sequentially, to find things that Lovász Local Lemma says exists when it says they exist. Okay, one more thing I mention, because it's going to be connected to distributed computing, which I'll be going on to shortly, is we can consider the Lovász Local Lemma as a graph problem. even though its definition doesn't inherently have any graph in it. And the way we do that is just we say our bad events will be the nodes in the graph, and we'll put edges between bad events that are dependent on each other. So in this case, we had these bad events, and we don't care about the underlying random variables anymore. We're going to kind of forget that they exist. We'll just look at the nodes, which are the events, and we'll draw edges between nodes that share random variables. So this one on the left here, for example, they both depend on this diagram here. So we draw an edge between them, these are dependent. And what we get is a graph. Okay, and from the definition of the Lovász Local Lemma, we know that this graph has maximum degree D, because that's what D was defined to be. Basically, D is the maximum number of other events that an event can depend on. And we've drawn edges between events that are dependent. So now it's the maximum number of edges that are adjacent to any particular node. Okay, so this gives us a graph with n nodes, a maximum degree D. Right, so I'll stop there on Lovász Local Lemma and go over to distributed computing, which is the other half of the title that you need to know about, before I can tell you what I'm trying to tell you. So distributed computing, and in particular the local model, is a model that I work in quite a bit. The purpose of it is that it's meant to model situations where you have some big network of computers, and these computers are trying to solve some problem collaboratively. So we're abstracting a lot here, it's a very abstract model. There are a lot of problems with trying to do stuff on, for example, the internet about security and faults and whatever. We're ignoring all those, sweep them under the rug. We're just really looking at what's possible if everyone is honest and their computers all work and they talk to each other. But you have to do this computation not as a sequential overview of someone who sees the whole problem and just tries to compute the solution. Instead, you have your problem, your graph, divided into a lot of different parts. Each part can only see a small local part of the graph, but you have to communicate and collaborate to solve some problems. Okay, so more formally, that looks like this. We have some input graph on which we're trying to solve some graph problem. I've put a couple of parameters here because that's what we'll care about. So this graph has n nodes, maximum degree delta. And the distributed part is that we are solving some graph problem on processes, but these processes are the nodes of our graph. So each node of this graph is a computer that can do something. And we have to solve our problem by collaborating with communication. But the local part of this is that you're only allowed to communicate with nodes that are directly adjacent to you in the communication graph. So you can do whatever computation you like, you can send whatever messages you like, but you can only send messages to guys who are adjacent to you in this graph. Which means, we're doing this on the internet, we can try and solve some problem here, but our computers can only send messages directly to each other in the room. Obviously, if you want to send a message to someone far away, you can do that, but it takes a long time because it has to bounce around a load of other routers and computers before it gets there. So in one round, you can only talk to your immediate neighbors, but if you want to talk further, you just take more rounds and relay messages. And our goal here is to solve some graph problem in the minimum number of rounds. So talking to people the minimum amount of time. And solving a graph problem here means that we each have some local part of the output we have to compute. For example, like a color in a graph coloring problem, or like whether we're in an independent set or something like that. We just have to output our own local output, but overall the output has to be valid. That's the usual formulation of the local model, but an equivalent way of thinking about it, if you don't really care about distributed computing and you care just more about like existential statements and graphs and things, is, okay, assume again we have our input graph here and nodes of the processes. Now assume a different kind of situation where we are one of these nodes in the graph, and we will just immediately see some ball around us of some radius r. And from that ball, and nothing outside of it, we don't see anything outside this ball. There could be, and in this example, there's only one computer out here, but this could be a small part of the graph. There could be a much bigger part of the graph going off here. We don't ever see that. We just have to make our output decision based on this ball around us. And then these output decisions have to be consistent across the whole graph. And again, the goal is to minimize R here, where R is the radius of the ball. And this turns out to be equivalent to running an R-round local algorithm. Because in a local algorithm, the best thing we could do would just be to send all the information we have every round. There's no reason not to, because the model doesn't restrict how much information we send. And that means basically in R round, you can see everything there is to see in your R radius ball. but you won't get any information from beyond your R radius ball because that would take more than R rounds to get to you. Okay, so a local algorithm is equivalent to having some radius ball that you see everything, and beyond that you see nothing. Can you still make consistent output decisions from just that part of the graph? So though it's, it comes from a kind of message passing framework, you don't have to think about it in terms of message passing. You can think about it in terms of an existential property of algorithms on graph. How much of the graph do you have to see to be able to make a consistent output decision? Okay, what's the connection between the local model and the Lovász Local Lemma? There's an obvious answer, which is that they both have the word local in them. Job done. But actually, this is not just some semantic coincidence. Local really means a very similar thing in these two names. In the Lovász Local Lemma, it's local because in your dependency graph of your bad events by definition are only dependent on the ones they're adjacent to in the dependency graph because we drew edges precisely between bad events that were dependent. And that means if you have some algorithm for the Lovász Local Lemma that finds variable values, then probably that algorithm is like the output it gives some variables of some particular bad event are probably only going to be dependent on events that are relatively close in the dependency graph. Because ones far away completely independent, they don't really affect what you're doing. It's only ones that are nearby that are likely to affect what the variables have to be for this particular event. And in the local model, we have nodes only communicate with directly adjacent nodes. And if you run a local algorithm, then your outputs for your local algorithm have to depend only on nearby nodes because you can't see the nodes beyond that. So you can't, even if you wanted to, you can't depend on far away nodes. Okay, so the local here means a very similar thing, which is that if you run an algorithm, then your output has to depend on stuff that's nearby, and it can't or shouldn't depend on stuff that's far away. Yep.
Question. It seems like you're defining bad and independence as a matrix on the left-hand side, like how far it is. If it's too far away, it's independent. I mean, is it really like properly formalizable or just an intuition?
In which, in the local lemma?
Yeah.
So I mean, it's your bad events are dependent if they're not immediately adjacent. But if you run an algorithm for the Lovász Local Lemma, then that algorithm will probably be, in one round you run the algorithm, then immediately adjacent nodes might resample their variables that will affect you. But if the algorithm then carries on, nodes adjacent to them will resample nodes, and now there'll be like a chain of distance to nodes that might affect each other. So it's not quite as formal a statement. But if you had a distributed algorithm for the Lovász Local Lemma, which we'll see shortly, then it would be a formal statement that if you have a distributed algorithm that solves the Lovász Local Lemma, then it's really true that the variable values you end up with would have to depend only on things that are nearby in your dependency graph.
Nice.
Okay, so I've got an example here of more concretely how these things are related. This is the most simple problem I can think of where the Lovász Local Lemma is useful in the local model. So the problem is the following: we have a graph. We'll assume it's delta regular just for ease. It doesn't have to be, but so it's a delta regular graph, which this example isn't. But anyway, on n nodes, and we'll care about the situation where the maximum degree of the graph is much lower than the total number of nodes in the graph. So you've got some really big graph, but locally you're only adjacent to a few people. So on the internet, for example, the internet's massive, but in this room, the people we're directly adjacent to, there's only a handful of other computers. And what we want to do, the degree splitting problem, and by the way, degree splitting problem is kind of used as a tool for other things. It's often used for edge coloring. This problem is just that we want to color the edges either red or blue of this graph. So the output is just for each edge, we have to output either red or blue. And we want to do this in such a way that about half of the adjacent edges of each node are each color. So for any node in here, you want about half of its edges to be red and half of its edges to be blue. I've been a bit vague about what half means here, but we'll see exactly what we can get on the next slide. So that's the problem. We just color the edges red or blue, and we want to do this in a way that is roughly even for each node. So this is an example here, and in fact, I think in this example, if I did it right, there's at most a difference of 1 between the number of red and blue edges adjacent to every node, which is stronger than we're going to be getting with most local, but in fact, it does exist. Okay. We want to do this with a local algorithm, and in fact, I'm going to ask for a very simple local algorithm that only takes one round. So what's the best we can get with a one-round local algorithm? Can anyone think of a local algorithm that would give you something that would be okay?
Random color.
Yeah, just choose the edges uniformly at random, and then output what you chose. So very simple algorithm. And this gives us something that's often not too bad. If we ask for like high probability in n, so we want we're going to say that our discrepancy is going to be some amount, and we want to say that this holds for all of the nodes in the graph, and we want to say that it holds with high probability in n. Anyone remember from any probability inequalities what kind of bounds you get here on how far away from delta over 2 your red or blue edges would be? Might be asking you a bit much for a Tuesday morning. Or at least what bound you would use to find that. Yeah.
It's not a root delta, like.
Yeah, it's about root delta by a Chernoff bound. In fact, it's root delta log n to get high probability here. And yeah, so you just get a Chernoff bound. You get with high probability in n, this happens at every node. And then you can take a union bound over all the nodes, and then you get with high probability, this happens for every node in the entire graph. Every single node will have at most its discrepancy here. Okay, and if n isn't too big, then maybe we're happy with this. But if you remember, I said we care about the situation where n is much bigger than delta. Possibly, delta might be a constant, and we care about n as n goes to infinity. And in that situation, this isn't great because we have an n here that we don't want. And okay, it's a log n, but still, if n is going to infinity and delta is a constant, this could be much bigger than delta. Okay, so we want to try and get rid of the n here. We want a bound on the how far away we are from a fair degree splitting that only depends on delta. And we can get that with a Chernoff bound. We can replace the n with a delta with a Chernoff bound. But the problem with this is that then Chernoff bound only gives us a probability that this actually happens of like 1 minus delta to the minus 2. Minus 2, by the way, is kind of arbitrary here. This could be any constant, but minus 2 is sufficient. And that means that this will work for most of the nodes, but there will be some smallish fraction, or not that small fraction, maybe if delta is very small, of the nodes for which they don't satisfy this, and for which they have a bigger discrepancy between their red and blue edges. And that's a problem because when we run a local algorithm, we want it to give some particular property at every node in the graph. It's not enough for us to get this property in most nodes in the graph. Okay, so that's the problem. We run a local algorithm, in this case a one-round local algorithm. It works most of the time, but its success probability is dependent on delta, which could be much smaller than n. And that means that there is some non-trivial fraction of the nodes for which it doesn't work. And that's where the Lovász Local Lemma comes in. So the Lovász Local Lemma we can set up now as follows. We have bad events, which are when a node has more than this many red or blue edges, has more than this discrepancy between its red or blue edges. That's what we want to avoid, that's bad. We're trying to make sure that every node has about the same number of red or blue edges. And there's n of them because there are n nodes in the graph, and we have one bad event for each node in the graph. And we have a bound from Chernoff on how likely this event is to occur. And we also have this bound D on the dependency degree because two events are dependent only if they share an edge in our input graph. Otherwise, this statement here is about a completely different set of edges, so they're independent. So the dependency graph is exactly the same as the original input graph. Nodes are dependent precisely if they share an edge, which means they're adjacent in the original graph. So we have P and D here, and so long as delta is at least 3, then this satisfies the Lovász Local Lemma criterion. And then the Lovász Local Lemma says it is possible to find a satisfying solution, which is a coloring of the edges, so that every node has at most this discrepancy between red and blue edges. Okay, again, that doesn't necessarily help us that much, but if we have an algorithm for the Lovász Local Lemma, and we run this algorithm, and this is a distributed algorithm, then this distributed algorithm for the Lovász Local Lemma will find us a set of edge colors that satisfies this for every node. So it will get rid of all the nodes that didn't work, it will find something that works at every node in the graph, based on this kind of underlying random process that only works for most nodes. And okay, I'll carry on a bit, but so that's should give you an intuition for why the Lovász Local Lemma is useful. We have to kind of formalize what we mean by a distributed algorithm for the Lovász Local Lemma. And for that, we'll set up, so we'll, in this case, our dependency graph will be the same as the input graph for our local algorithm. That's not always the case, but actually it doesn't matter that the dependency graph is sometimes a bit different from the underlying graph. So I'll kind of split that under the rug. So assume that you have this dependency graph for your Lovász Local Lemma, and that's also your input graph in the local model. And then obviously these nodes in your local model correspond to the bad events that you're trying to avoid in your graph problem. As they did in that previous example, that each bad event was attached to a node. And nodes that represent events that are dependent are allowed to communicate directly. Okay, it's not really obvious why we might set up this way, but if you're trying to satisfy or avoid satisfying two events, and if these two events share variables, then they're going to have to agree on what that variable value should be, which means they'll have to communicate. If they don't share variables, then they won't necessarily have to talk to each other, so we don't make them adjacent. Then we have this same setup as usual in the local model with n nodes. For convention purposes, we'll say the maximum degree is now D, where D is the Lovász Local Lemma dependency degree. It's basically the same thing as delta, it's just tradition that in the Lovász Local Lemma it's called D, and in the local models it's called delta, which is maybe a bit unfortunate. If we'd have worked out in advance that this was going to happen, we'd probably have set them to be the same thing. But D basically is delta here. Okay, and then we can say that we want an algorithm to solve the general Lovász Local Lemma, which is whatever Lovász Local Lemma instance we set up, we want to have some algorithm that works on it, sets all the variables, so that if there exists a satisfying solution by the Lovász Local Lemma, we will eventually find one in some number of rounds. And if we could do that, then this can solve any problem like degree splitting that we just saw, that can be reduced to the Lovász Local Lemma. So if we had an algorithm for this, it would out of the box just solve us degree splitting in the way we just set up. And in fact, there are a bunch of other problems that this can be applied to. So a distributed Lovász Local Lemma works kind of like a meta algorithm. You have already a randomized algorithm, but it doesn't work everywhere, it fails at some nodes. And then you apply to that your out of the box Lovász Local Lemma algorithm, and suddenly it fixes this algorithm to work everywhere. So that's why the Lovász Local Lemma is quite integral to the local model. It's actually usually the case that if you run a distributed algorithm for only for less than log n time basically, then it will only give you correctness at each node with something that's like polynomial or exponential in the degree, and won't be a function of n, or at least won't be a high enough function of n to take a union bound over the whole graph. Which is exactly what we saw. If we wanted that tied the bound on the discrepancy, Chernoff only gave us a probability bound that each node works that depended on delta and not n. And then we apply the Lovász Local Lemma algorithm that we don't know exists yet, but we'll see one. And it will set the randomness of this other algorithm that we already tried in a way that fixes all the nodes that didn't work before. So it kind of amplifies your success probability for each node from not enough, some function of delta, to high probability working over the whole graph. So it's basically a probability amplification algorithm. And it turns out that this gives you some results in complexity. Distributed complexity is usually studied in graphs of constant degree, so that they hold in constant degree, but it's been shown that this is or really the complete problem for quite an important family of problems of complexity gaps in local model in bounded degree graphs. So basically, in bounded degree graphs, if you have an algorithm or some problem that can be solved in less than logarithmic time, then you can show that you can use a Lovász Local Lemma on it and solve it in whatever time your distributed Lovász Local Lemma algorithm takes. So every sub-logarithmic time problem reduces to the Lovász Local. So it reduces to or reduces from. I always get it the wrong way around. Anyway, LLL basically is a complete problem for the class of problems that can be solved in less than log n time in local. Yeah.
How is randomness distributed? Is it like shared randomness? Or...
No, all local randomness. So that's, in fact, usually that doesn't matter. But yeah, everything is local in the local model, so each node gets its own source of random bits. And if you want shared randomness, then you have to send messages around to.
But you're looking at log n rounds, so you cannot send randomness.
Yeah, you can't send randomness across the whole graph, but yeah, generally you don't need to because everything is local anyway. Yeah, I can't think of any examples where it actually matters that it's.
For example, when you color THs uniformly at random, the two nodes has to agree on the randomness, right?
Yes, so yeah, to color an edge, both the endpoints have to agree, but that doesn't require shared randomness, it just requires you can assume that the nodes have IDs because if not, they just randomly pick one at the start and if you pick from a big enough space, then it'll be unique. And then you just say, okay, whichever endpoint of the edge has higher ID, that endpoint is responsible for coloring that edge. And then he just chooses randomness and the other node doesn't drive. So yeah, you can share randomness between adjacent nodes and in general between however far your algorithm is allowed to see. You can't share randomness beyond that distance, but you don't really need to. Okay, so this has been studied quite a bit. So Moser and Kardosh's results, it didn't actually write that it had a distributed algorithm for this, but if you read between the lines, you can very easily get one from their parallel P1 algorithm. This just resample, like if you have bad events, resample their variables. You have to do it in a slightly more distributed way, but it gives you a simple algorithm that runs in log squared event time. And this, for a slightly weakened LLL criterion, but I'll again sweep that kind of under the rug, so it will require me to introduce too much stuff, has been improved to log n time by Petty and Su. And this is kind of the best you can do for these types of resampling algorithms where you sample all the variables once, and then you look through what you have to fix, and if there's some variables you have to fix, you just sample them from the distributions again, re-roll the dice until you get something that works. But there's another side of algorithms, and in fact, a side of algorithms that came from sequential algorithms that were prior to Moser and Kardosh. So there was, I think, an algorithm by Beck on which these distributed algorithms are based, called shattering style algorithms, or at least I call them that because they involve a process called shattering. So the first one was by Fisher and Ghaffari, and this takes time, which is a polynomial in the dependency degree of the graph, but then only poly log n in n, and n is often much bigger than the dependency degree of the graph, which is delta or close to delta. So when your degree in your graph is low, this is substantially better. And my result on this problem is to improve the dependency here on the dependency degree, but still this remains polynomial, so this only is good for when your degree in your graph is fairly low compared to n. And there's also a lower bound, and in fact, this was one of the, well, it was the first lower bound that introduced a new technique in lower bounds called round elimination. Okay, some people might dispute that because it was maybe a rediscovered technique. But this was a major lower bound which started a whole chain of lower bounds for other problems. And this lower bound says that you can't solve the local lemma, even actually for a very simple, like a simpler special case called Lovász Local Lemma, in less than log n time. So, okay, if you don't care about polynomials, then this part is kind of optimal, but this part is maybe not. And this is not optimal. We might hope to get exponentially better and get down to log n. Okay, I'll quickly show you how these algorithms work. So with Moser and Kardosh's algorithm, we've already kind of seen. You just sample all the variables once, and this makes some of the bad events satisfied, and then you just have to resample those bad events. But when you resample those bad events, you change their variables, and the adjacent events depend on those variables. So you might make adjacent events bad. So you have this kind of cat and mouse game where you resample something, and then you resample something else, and you resample over there, but it turns some other events bad that were previously not bad. All the events bad. It makes them events satisfied that were previously not satisfied. And you keep doing this, and the analysis of Moser and Kardosh tells you that eventually this process will terminate. And to do this in the local, rather than just sampling one event at a time, which obviously you can't do because you can't look at the whole graph and say, I'll pick this event. You're like a part of a small part of the graph, you can't see the whole graph. So in fact, what they do is calculate a maximal independent set and then sample all of those bad events variables at once. And that's the part that Petty and Stu sped up you to log n by doing something that's not quite a maximal independent set, because this algorithm spent a long time computing maximal independent sets when you don't really need to. But that's the idea of it. You just you have a few of these going on at the same time, but basically you're just resampling the variables of satisfied bad events. And that's why I call them resampling style algorithms. Both of these I call resampling style algorithms. The other style of algorithms are the ones like Richardson and Gavari's algorithm, where you don't sample all the variables to begin with. You just slowly sample some of the variables with the aim that you never actually make any of the events satisfied. So you start going off like this. So what they actually do is calculate a coloring of the graph so that no node has more than one adjacent node of each color, but that's not too important for what I'm going to say. You slowly sample the variables in the graph like this, and at some point you might notice that an event gets dangerously close to being satisfied. And at that point you say, okay, I'm going to stop sampling any of the variables of that event because I'm getting too close to satisfying this event. And I'm going to freeze this for now. I'm going to obviously have to sort it out later. But then I just carry on sampling things, but not the dependent variables of this event. And again, you carry on doing this until something gets too close to being satisfied. And if it gets too close to being satisfied, you freeze the remaining variables. And okay, then you carry on until you've sampled everything that's not frozen. Then at some point you've got to go and actually sample the frozen stuff. But it turns out that if you do this process correctly, you can show that this graph of frozen things shatters into small pieces. I won't go into too much about what I mean by small here. But if you have this whole big graph, you will show that only small connected components in here have to be frozen. Most of the graph you can just sample all the way through until you get to the end and everything works. Small parts of the graph you can't, you have to freeze it. But because these parts are small, there's a deterministic algorithm actually that you can go back to and solve the problem on these small connected components quickly because they're small. And that allows you to, so that's the part that takes this log n time, and the first part takes you polynomial in d time by t is the 20th degree. And my algorithm is sped up this first part of the process, this gradually sampling stuff, by sampling a bit less gradually. And the difficulty there is you have to make sure that you don't break anything, you don't sample too quickly, because if you sample too quickly, then events can become bad and then you're stuck. Events can become satisfied and then you're stuck. So those are the two algorithmic approaches. First one, sample everything and then just resample stuff until everything's fixed. The second one, sample gradually so that you never make any event satisfied. And if events get too close to being satisfied, set them aside to solve later. And it turned out that graph of stuff you set aside to solve later is in small components, so it turned out to be easier to solve. Okay, and the major open problem, which is what I wanted to get to, so I'm glad I got there in time, what I've been trying to do for a while and haven't particularly got that much closer to, is there an algorithm that works in at least polynomial game bounds in any graph, so even when dependency degree is not constant, is some function of n. And this is what I've been trying to do. And I'm kind of encouraging you to try and do it too. The reason this is hard is that both of these algorithmic approaches, actually, I'll stop that part again. Both of these algorithmic approaches have a barrier that seems like it's going to be hard to get this kind of complexity. The resampling style algorithms, the barrier is the following. When we resample stuff, it can cause a chain of events that you make satisfied, then you have to sample them, but you make their adjacent event satisfied, and you have to resample them. And the analysis kind of inherently seems to rely on the fact that these chains can be of length up to log n. So there can be, and there are, when you actually do this, chains of log n events where, to begin with, like only the first one on the left is satisfied. But if you resample that, it makes the next one satisfied. If you resample that, it makes the next one satisfied, and so on. And you have to do these sequentially because you don't know which ones are going to become satisfied. You don't know in advance that you're going to have to sample these later, otherwise you can do it now. You only know when you sample this one that this one suddenly becomes bad and suddenly becomes satisfied, and you have to resample. So you get this long chain of dependent things that you have to do, which you have to do in sequential order, which means it takes time, which is at least the diameter of this chain, and the diameter of the chain can be log n. So for a local algorithm, this seems like a major barrier here. There doesn't, as far as we know, there's no way of shortening these chains. And if you can't shorten these chains, you can't hope to do this in less than log n time. And for the shattering style algorithms, the problem is that you have this first step where you have to gradually sample stuff. If you sample anything too fast, then you can have events that become satisfied immediately, and that's a problem because you have no way to fix them. So if you do too much sampling at the start, you'll get some events here that had a lot of their variables sampled, and they became satisfied. and that's bad, we have to do something about this. But if we now try and resample then we get these long chains that we had in the resampling style algorithms. So we can't just sample some stuff and then resample these. If we did, we would basically be going to the same problem we had here, because we'd be doing resampling. And this means that you seem to need something which is polynomial in D, at least D over log D, which is what I got. Maybe you could slightly improve it, but as far as we can see, you can't improve that much. You need to spend at least roughly D steps sampling the variables. Otherwise, you will be making things satisfied too quickly to stop. Okay, and that's the problem I've been trying to solve, and you might have to try and solve too, 'cause it's quite a fun problem. What I have got so far is the following. It turns out that if you're trying to do a local algorithm and you look at what region in the graph a node has to base its decision on, I've been able to show that a node only has to look at a small region to make its algorithm. And in fact, the size of the region is this thing, which is precisely the size of the log n radius ball. So a node only has to look at a ball which is the size of its, or an area which is the size of its log n radius ball to make its decision, which is almost what we needed, but not quite, because it isn't this log n radius ball, which would give us the log n time local algorithm. It's some longer but thinner shape. So you have to only look at a ball of the right, a area of the right size, but unfortunately it's not a ball, it's something that can have a big diameter. And that's no good to get as a local algorithm. It does help us in some other models, but not in local. So that's where I've kind of got to at the moment. This is still work in progress that I'm working on. But still, I thought this was quite interesting that you can show that your output decision, you know that it only has to depend on this small area, but unfortunately this small area is long and it may be thin, but it's long and not concisely contained in a ball. Some other open problems, if you think this is too hard, which might be a good assessment of it, is, okay, maybe we can't do this straight away for the general Lovász Local Lemma, but the whole point of doing this is that we can apply it to other algorithms for coloring problems and other stuff. So can we at least get this working for some specific applications, like some coloring problems? For example, degree splitting, which is one of the kind of simplest special cases of Lovász Local Lemma. All the way through, I've been talking about the metric Lovász Local Lemma. There's an asymmetric version, which is more general, where it could be the case that your bad events don't all have the same probability of being satisfied. Some of them might have high probability of satisfying, some of them might have low probability of being satisfied. There's a more general statement of the Lovász Local Lemma that takes into account, which again might be useful in the distributed setting, but for simplicity, that mostly hasn't been studied in the distributed setting. And also, I've been talking about the local model, but there's a load of other distributed, parallel, possibly beyond models for which it might be useful. So, for example, congest, where you can only send small messages, or like local computation algorithm, which is more like the previous slide, where you care about the size of the shape you have to look at rather than the radius. Or parallel models like PRAM or like massively parallel computation. A bunch of the same techniques would probably be useful there. Okay, I think that's about time, so I'll stop there. Thanks for listening, and ask me if you have any questions.
Thank you very much for the talk. Do you have any questions in the room? There should be at least one on Zoom, so raise hand. Anyone has more questions?
Yeah, so initially we were assuming that all the events had probability of most P. And at the end you said there could be variants which that wasn't the case. What those variants look like? Is it that the average probability is at most P, or do you depend on no spikes or something?
So there's some more complicated at least formula saying that if they have a higher probability of being satisfied, they have to have lower degree for it to still be solved.
Right.
But it's kind of average over the whole graph rather than individually. So you can have like one event with reasonably high probability and high degree, but over the whole graph in general, if you have events with high probability, they have to have lower degree.
So it's a bound on probability times degree total, as it were.
Yeah, essentially, yeah.
Okay, thanks.
Any other questions? Yeah.
Just the carefully kind of balanced event dependencies and like the asymmetric constraints there? Like, where do you see this in terms of the theorem being eventually applicable, kind of maybe to practical challenges we have today? It's just overcoming that challenge in this theorem.
You mean the asymmetric?
Yeah.
Yeah, so I mean, mostly what the symmetric version, mostly it's applicable to coloring problems, for example, where you have to color with, like, so for example, delta plus one coloring, okay, delta coloring, where you have a number of colors, which is like the maximum degree in the graph. But actually that's often not the case, and there are algorithms, for example, for degree plus one coloring, where you're trying to color nodes or edges or whatever. And the number of colors you're allowed is only something like the degree of that node, which is a more kind of local setup really, because it's in some sense not really local to assume that you even know the maximum degree of the graph. And there you would think the asymmetric lemma, local lemma might be more applicable, because then you just need a bound on, you know, what's my degree, rather than having to know the maximum degree of the graph and have that number of colors. So yes, it would hopefully be more applicable to this more local style of problems where all of the constraints are just about what you can see under your local neighborhood. But as far as I know, it hasn't actually been used for anything in the local model so far.
Yeah. So what would be a conjecture for the complexity of the LLM?
For me, it changes on a week by week basis.
So it should have some term dependent on the.
Well, if you could get, you know, if you got it to polylog log n, then probably that would subsume the algorithms that contain term with d in it. So that would just be the best complexity. I mean, there's a lower bound that you can't get better than log n, even with some higher term.
The upper bound doesn't assume on d, right? The order log n upper bound.
The order log n doesn't know, so that's, in fact, it gets better with d. So it's basically order of log base d of n.
So do you think there can be a low bound with this also like omega t to the epsilon? No, I guess. Because that would be like refuted by the order log n upper bound.
Yes, yeah. So yeah, there might be some cutoff where up to some value of d is that, and up that's not, but there'd be no straightforward lower bound saying it would have to be polynomial on d. Yeah, I mean, most of the time I spent on this, I thought possibly the algorithm could be improved, because that was what I was trying to do. When it's going well, I think the algorithm can be improved. When it's not going well, I think the lower bound can be improved. But
did people look at this from the other point of view, like say two-party communication?
You mean getting like a communication complexity low, and that would be kind of difficult because you can't really get any bound on how much information you would need to communicate. There's nothing really saying that you need information from anything beyond your local variables.
Yeah.
I don't know how you would really set up a situation where you could get some communication bound. Probably you would have to use similar techniques to what the lower bound already does, which is this random elimination thing where you say, okay, if I can solve this problem in t rounds, then I can solve this other problem in t minus 1 rounds. And then you keep going until you get to the point where I can solve this problem in 0 rounds, but then you show that this problem can't be solved in 0 rounds, which means your original problem can't be solved in t rounds.
That's just random.
Yeah, and that seems like the only way you can really get a grip on this from a lower bound perspective, but also it's hard to see how you could get better than log again from that. At least randomized. So it also gives you a deterministic lower bound of log n. So deterministically we know we can't get better than log n, but randomized potentially we can.
More questions? Can we check online?
Yeah, sure. So I think Prudence had her hand up. So Prudence, I think you should be able to talk now. If you'd like to ask your question.
Sorry, I think I raised the hand incorrectly. Yes, I didn't see how I lowered it, so I don't. But thanks for the talk. Thanks.
Okay, no problem.
Catherine, do we have anything else indicating a question from Zoom? Is there anything in the chat or no?
No, if anyone would like to ask a question, just raise your hand and I'll let you talk. At the moment, there's no hands
All right.
raised.
Well, let's thank Peter again for a nice talk.